In this video, I'd like to demonstrate how we can use Gauss's law in order to figure out the electric field in a particular situation. So the basis for this argument lies in symmetry. So I'm going to make a claim here. The claim is that if the charge distribution has a certain symmetry, then so does the electric field. Okay, so why should that be true? Why would the charge distribution being symmetrical mean the electric field also has to be symmetrical? Well, the reasoning is that if the charge causes the electric field, which is the way that we've been thinking about it up to this point, then the same charge must lead to the same electric field. And the way we defined a symmetry is that we make some change to the situation which results in it looking exactly the same. Okay, so if that's true for the charge, then I claim it has to be true for the electric field as well. Okay, so the situation I want to look at specifically is an infinitely long charged rod. So I can't draw something that is infinitely long, but what I can do is draw a segment of it like this, and then do some dotted lines to indicate that it keeps going. Okay. And so what is the property of this rod? If it's infinitely long and it's charged, that means it'll have infinite charge, so that's not very useful. But what we can do is we can define the charge density, lambda, which is the charge per length. Okay, so maybe we know it's got some number of coulombs per meter, and that is the information we know. Okay, so the first thing I want to do is consider the symmetries of the situation so that I can figure out what the electric field should look like. Okay, and there are several different symmetries. Let's look at a couple. Okay, so one of the symmetries is if I reflect it across this line. Okay, if I do that, then the rod ends up in the same place it currently is, and because it's infinitely long, it will look exactly the same. Okay, so I can flip the rod vertically. Okay, I could also, if I wanted, flip the rod horizontally. So I can draw this axis here, and I can flip it left to right across that line. Okay, or I could also rotate around the axis, and because it's cylindrical in shape, I can rotate it by any angle, and the rod will look the same. Okay, finally, and this one is a little more subtle, I also could shift the rod vertically. And the only reason that that one is a symmetry is because the rod is infinitely long. So if I shift it upwards, like a meter, well, it still looks exactly the same because it extends infinitely far in both directions. Okay. So how can we use this to find the electric field? Well, I have to figure out what patterns the electric field could have that are consistent with all of those symmetries. And it turns out there aren't a lot of options. We can actually figure out pretty much exactly what the electric field is going to look like just based on those. All right, so for instance, let's consider that we had an electric field that was pointing vertically. Now you don't expect this to be the case because of the shape that the rod is, but we can use symmetry to rule it out explicitly. Okay, so let's say the electric field looks like I drew. Well, if I consider the symmetry where I flip the rod vertically, then it would end up with an electric field downward like this. Okay, and that would be different. So if I change the rod in some certain way and it ends up looking exactly the same, then when I change the electric field in that same way, it has to look the same. And we see that is not true. Okay, so what this tells me is that I can actually rule out there being any vertical component to the electric field. Okay, so any component of the electric field has to not be vertical. It has to be sort of in the xy plane, if you imagine that being how this is set up. Okay, so let's then consider looking at the rod end on. Okay, so if I draw the rod looking at the end, then it's going to look like this, extending out of the screen and into the screen infinitely forever. Okay, well, so let's see about a rotation for the symmetry. So if I have an electric field that looks like this, well, as I rotate it, the electric field would have to look like that, and if I rotate it further, it would have to look like this and like this. Now, no matter how far I rotate the rod, I'm going to end up with those electric fields lining up on top of each other. But I also had the symmetry that I can flip it horizontally. So if I flip the electric fields horizontally, then I'm going to get a different result afterwards. Here I'll get one that looks like this, and here this one would end up over here, like so, and then the one that's on the left would end up on the right. Okay, and then this one goes like this. All right, so I get a different result flipping it. Okay, so what this means is I can rule out any component of the electric field that's going to be pointing clockwise or counterclockwise around the rod. Any component that does that is going to be eliminated because it's inconsistent with the rotation and horizontal reflection symmetries. Okay, so we can rule out clockwise or counterclockwise. We call these azimuthal components. Okay, so what that leaves is only radial components. We've ruled out vertical components, we've ruled out azimuthal components, and all that's left is electric fields that point directly towards or away from the rod. And if we assume that the rod is positively charged, then we'll know they'll point directly away. Okay, so that's pretty good. But there's one more thing that we can do with that translational symmetry. So let's imagine that I guess that the electric field points away, but then not with equal magnitude as it goes. Maybe it gets stronger as you go further down the rod. Well, this is a place where I can use that translational symmetry to rule that out. I can see that as I shift the rod up and down, the electric field at some distance from the rod has to be constant. Okay, so we can rule this out with the translational symmetry. Okay, so now we know exactly what the electric field is going to look like. It's always going to point radially away from the rod at every point near the rod. Okay, so now that was all just the symmetry argument. So let's start over with a fresh diagram. So I'll draw my rod here, which again is infinite, so I'm going to indicate that with these dotted lines, like so. And now I'm going to sketch in some electric fields, and I'll use this purple color for that. I know that the electric fields have to point radially away from the rod. So I'm going to try to draw this in perspective, like so. of like this. Okay. And I know that at other places along the rod it has to look just like that. So I'll draw another spot over here. Radially away. Like that. Okay. We know that's what the electric field has to look like just from the symmetry argument. Okay. So now what we want to do is figure out what is the magnitude of the electric field using Gauss's law. Okay, so remember, what we're trying to do when we use Gauss's law is we want to come up with a surface that is always either parallel or perpendicular to the electric field. And there may be more than one choice, but in this case, the most straightforward surface that we can use is going to be a cylinder. Okay, so what I'm going to do is I'm going to have the cylinder centered on the rod like this. Like so. Okay, so that cylinder has three parts. It's got a top, a bottom, and then that curved side. All right, so the flux through the whole surface is going to be the sum of those three. It'll be the flux through the top, plus the flux through the side, plus the flux through the bottom. Okay, so we can calculate those three individually because we have chosen the sides to either be parallel or perpendicular to the electric field. Okay, so let's start at the top. The area vector for the top surface is going to point upwards. Remember, it has to point outward from the closed surface, and this is a closed surface, so the area vector for the top points up, like so. And the electric field points radially outward, so the flux through the top is 0. Similarly, for the bottom, the area vector points downwards, which means that the flux through the bottom is 0 because it's perpendicular to the electric field is perpendicular to the area. Okay, so the total flux is just the flux through the side. All right, and that's going to be equal to the electric field through the side times the area of the side, because along the side, the dA vector points outward, and the electric field vector points outward. So those are always in the same direction because of the shape of the surface that I chose. Okay. And the area of that curved surface, well, if you imagine just slicing along it and then unrolling, what you would have is a rectangle. And the rectangle is going to have a length that is just the circumference of the cylinder. So that'll be 2 pi r. And then the height of the rectangle is going to be L. So that's the area times the electric field E. Okay. Now using Gauss's law, I know that the total flux is equal to the charge enclosed over epsilon naught. All right. And the charge enclosed is going to be given by the charge density. So remember, I have lambda equals Q over L. So basically, whatever the length of this cylinder is, which is the same thing that showed up in the area, that's what's going to give me the charge. So the total flux is going to be lambda L over epsilon naught. Okay, so then finally, I just set those two things equal to each other. The total flux, which is lambda L over epsilon naught, is equal to 2 pi r L times E. And then if I solve for E for an infinite rod, then what I'm going to get is the L's will cancel, and I'll have lambda over 2 pi epsilon naught r, where r is just the distance from the rod. Okay. So you can see that this calculation is dramatically easier than the integral that we did to find the force from a charged rod. It took 2 pages essentially to go through all the calculations and the arguments for that. Here we use symmetry to determine what the electric field should look like, and then it took approximately 4 lines of calculation to find the electric field for the infinite rod. And you can check that the 2 calculations are equivalent by taking the finite rod and taking the limit as L goes to infinity. And if you do that right, then it should come out to the same form as this one. Okay, so we're going to use the same strategy in a couple of other cases. First, we use symmetry to figure out what the electric field should look like. Then we choose a Gaussian surface that's either perpendicular or parallel to the electric field everywhere. Then we explicitly calculate the flux and set it equal to the charge enclosed over epsilon naught.